All right, we are working on 9.8, just extra practice here. So the directions say find the radius and interval of convergence for the given power series. So remember, your options are usually ratio test, maybe geometric series test if it applies. I don't think it does for any of these. So first I'm going to do the limits as n approaches infinity of the absolute value. So that ignores the negative 1 to the n of the n plus 1th term divided by the nth term, so multiplied by the reciprocal of the nth term. All right, so cancel things out. So 2 to the n over 2 to the n plus 1 leaves me with a 2 to the first in the bottom. X plus 1 to the n, x plus 1 to the n plus 1 leaves me with x plus 1 to the first. So this just comes down to x plus 1 on top and 2 on the bottom. There are no n's left here. So this series will converge by the ratio test if this expression in its absolute value remains less than 1. And that means that we can set this expression to fall between negative 1 and 1. So let's solve this for x. So multiply by 2. Now, when you get to this line where you've isolated the x minus c between two numbers, that shows you your radius. So I can say right now the radius of convergence is 2. And then solve for x to find the interval. So subtract 1, you're going to get negative 3 is less than x, which is less than 1. But remember, you need to check these endpoints. Since this is not just a straight geometric series, it could be that plugging in the negative 3 or the 1 gives us some sort of alternating series or something else that will converge at the ends. So check that. I'm going to show the checking over here. So let's see. So let's check if x equals negative 3. For a free response question, you need to show what that series would become. So if you plug negative 3 in for x, you've already got a negative 1 to the n. Negative 3 plus 1 gives me negative 2 to the n, and you're dividing by 2 to the n. So now this right here, you can say this is the same as negative 2 over 2 to the n power. All right, so essentially what you have is a series, let me go below this. So if we simplify that, we have negative 1 to the n times negative 1 to the n. That's just negative 1 to the 2n. And really negative 1 to the 2n, that's just always positive, right? You'll always be raising negative 1 to an even power. So really I could just say this is the series of just 1. Add 1 infinitely many times, that's definitely going to diverge by the nth term test. So we are not including x equals 3 in our interval. Check the other side. Just because you don't include one side doesn't mean that the other side gets excluded as well. So if we plug 1 into this expression, we already have a negative 1 to the n. That would make 1 plus 1 is 2 to the n over the 2 to the n that's already in there. So those divide out to 1. And even though this is alternating, the terms are just going to keep going plus 1, minus 1, plus 1, minus 1. So you'll never get a finite sum. It will either be it'll either be 1 or 0 or something. So this also diverges by the nth term test. So our final interval of convergence is just any x value between negative 3 and 1, but not including those n's. If you want to use interval notation like parentheses, negative 3 to 1, that's okay too. All right, so let's take a look at the next one. I'm going to use the ratio test again to begin figuring out our interval of convergence. So this will be x to the n plus 1 over n plus 1 squared times n squared over x to the n. What will we be left with? So the x's will cancel to x to the first. And then you've got n squared times x over n squared. So the n squared over n squared will become 1. So this just leaves you with the absolute value of x. And that would converge. This power series converges by the ratio test if the absolute value of x is less than 1. You don't have to write that every time. You can jump straight to x being between -1 and 1 if you want to. I need to double check these endpoints though. So let's check the ends here. So if x equals -1, you need to write the simplified series that would create. So we would have -1 to the n over n squared. That's an alternating series. The limit as n approaches infinity is 0. So this would converge by AST. And what if x equals +1? That would give us the series from 1 to infinity. Again, to get credit for this on an AP test, you need to don't just write a sigma or just the expression, especially if you just write this. That is nothing. So you've got to do all of this correctly. If you practice it in your homework, you will do it correctly on the AP test. So when I plug 1 to the n in, I just get 1 on top over n squared. But this also is a convergent P series. All right, so both ends converge here. That means that we are now including -1 to +1. Remember, the interval of convergence just means you've got this power series where if you were to expand out terms, you'd have a bunch of x's in the terms. So as long as x is a number within our interval of convergence, you will get a finite sum to that infinite series. If x is outside of this little domain of numbers, then the series will not converge. It will diverge. All right, next one, the limit as n approaches infinity of the absolute value. So remember, you're plugging n plus 1 in for n. So this will become 3n plus 3 plus 1. So this will become x to the 3n plus 4 over 3n plus 4 factorial. We're multiplying that by the nth term, which is 3n plus 1 factorial over x to the 3n plus 1. So these will cancel to x cubed because 4 minus 1 is 3. And for the factorials, remember 3n plus 4 factorial is 3n plus 4 times 3n plus 3 times 3n plus 2 times 3n plus 1 factorial. So that 3n plus 1 factorial will cancel with that one, but we will be left with all of these terms. So we have x cubed over this like 27n to the third. So as n approaches infinity, this bottom heavy thing will come out to 0. So that's great when that happens because 0 is always less than 1. And so we don't have to solve for anything. This series will always converge by the ratio test. Oh, I just realized I didn't answer the radius for the last one. Sorry. So the radius was equal to 1. And we had our interval of convergence. So here, this thing converges always by the ratio test. So for all x values that are real. So what does that mean? It means our radius of convergence is infinity. And it means our interval of convergence is any x value from -infinity to infinity. And again, you can use interval notation. I'm just trying to be consistent, I guess. All right, number 4, let f be a function that has derivatives of all orders for all real numbers. Assume that these values are true. So notice that we are evaluating every function at 3. So even though it does tell me this in the problem, this is a center of 3. It's good to be able to pick that information out. Write a third order, n equals 3, Taylor polynomial for f at x equals 3. That's the center again. Use it to approximate f of 3.2. So first, let's go ahead and say f of x will be approximately equal to. Now, you don't have to show this, but just for the sake of the video, I'm going to go through what this is, what this means again. Remember, building one of these is like f of 3 plus f prime of 3 times x minus 3 to the first over 1 factorial plus f double prime at 3 times x minus 3 squared over 2 factorial. we're going third order, so f triple prime at 3 times x minus 3 to the third all over 3 factorial. So that's going to be what we use to approximate. Now, if you didn't write all of that out, that's okay. You can go right to subbing the numbers in. So f of x is about equal to 1 plus 4 times x minus 3 plus 6 times x minus 3 squared over 2 factorial plus 12 over x minus 3 cubed over 3 factorial. And we're supposed to approximate f of 3.2. So when I plug that in, 3.2 minus 3 is going to be 0.2. I'm also, in my calculator, I'm going to simplify these a little bit. So let's split this up. All right, so it's 1 plus 4 times 0.2 is the difference between 3.2 and 3. Plus, so 6 over 2 is 3. Oops, I meant to write plus there. 3 times 0.2 squared. And then 12 divided by 6 is 2. So plus 2 times 0.2 to the third. You don't have to simplify that. I'm just trying to save myself typing. But if I make a math error, then that's not great either. So just be careful. So 1.936. So f of 3.2 is about 1.936. Right? Write the second order Taylor polynomial for f prime at 3 and use it to approximate f prime of 2.7. So why is it second order instead of third? Now, all you have to do, remember, you're not coming up with like a series or a formula. All you have to do is take the derivative of the f terms. So take f of x and start taking derivatives of each term. The reason it's second order is because we're going to get down to a degree 2 polynomial, and that will represent the second order. So don't overthink it, I guess, is what I'm trying to say. So the derivative of 1 is 0. The derivative of 4 times x minus 3 is 4 times 1. Plus, now this was, I want to simplify this just so my life is easier. So this was 3 times x minus 3 squared. So it's going to be plus 6 times x minus 3 to the first. And remember, if we had to chain rule, if this were like 2x minus 3, we would have to make sure that we're incorporating chain rule too. So just be careful with that. I feel like that happened in my homework, maybe in the last assignment. Okay, and then what was this? This one was 12 divided by 6 was 2 times x minus 3 cubed. So this is also going to be plus 6 times x minus 3 squared, right? Right? Yeah, so 12 divided by 6 times 3. Okay, yes, that's fine. And then we need to approximate 2.7. All right, so putting in 2.7. Now, 2.7 minus 3 is negative 0.3. So again, you could just type it in with the like minus 3 built in there, but I'm just trying to save myself a little bit of typing. So negative 0.3 plus 6 times negative 0.3, and then we're squaring that. So I'm getting 2.74. So f prime of 2.7 is about 2.74. Does the linearization just means the approximation that you did. I know we didn't linearize because we were using curves, but that's what that term means. So does the approximation of f underestimate or overestimate the values of f of x near x equals 3? Justify your answer. So this is based off of concavity, right? So we have two scenarios. If a function is concave up and we use a tangent approximation, whether it's linear or not, the approximation will be an underestimate. If the graph is concave down and we use a tangent approximation, then our value will be an overestimate. It'll be above the graph. So how do we know about concavity? We look at the second derivative. So f double prime of 3 is equal to 6, which is greater than 0. So if the second derivative is positive, it means that f of x is concave up at x equals 3. So when we are plugging in values near x equals 3, like 3.2 or 2.7, we can say that the approximation is an, what did I say, concave up, an underestimate. I always have to draw the picture for myself because I can't keep it straight. Now, I referenced 2.7. I should have just said we're just talking about the 3.2 value. Okay, let's look at number 5. So we have this fourth order Taylor polynomial. This is for fourth order Taylor polynomial for function f at x equals 4. So that's our center. Assume f has derivatives of all orders for all real numbers. So, all right, so be careful with this one. This is a pretty common AP question. We're supposed to be able to get function values out of this thing. But remember that before this line, 7 was f of 4. So, that's my answer there. So f of 4 is just 7. That's easy. But the third derivative at 4 is not just negative 2. Because remember, the next line is f prime of 4 times x minus 4. And then the next line is f double prime of 4 times x minus 4 squared over 2 factorial. And so f double prime of 4 over 2 factorial came out to 5. And then same here, f triple prime at 4 times x minus 4 to the third over 3 factorial. F triple prime of 4 over 3 factorial comes out to negative 2. So we have to do some math on this and say, okay, we know that f triple prime of 4 over 3 factorial is equal to negative 2. We have to multiply 3 factorial over there. So remember, 3 factorial is 6. So f triple prime of 4 had to be negative 12, negative 2 times 6, for this to work out to be a negative 2 in front. So be careful. They love to give us those questions because they're counting on you just saying, the answer is negative 2 and going on from there. All right, write the second order Taylor polynomial for f prime at 4 and use it to approximate f prime of 4.3. So again, use the fourth order polynomial they gave you. We're not trying to write a series with a sigma or anything like that. We're just trying to say, okay, f prime of x is about equal to second order, because there are no zero terms, I should say. There are no zero terms. So we just stop when we get to a degree 2. So the derivative of 7 is 0. The derivative of this linear term will be negative 3. This derivative will be plus 10 times x minus 4 to the first. And chain rule, technically, the derivative of x minus 4 is 1. And then the next term will be minus 6 x minus 4 to the second. So I'm stopping there because this is my second order Taylor polynomial. And then use that to approximate to, 4.3. All right, so I hop over to my calculator and I type this in. So negative 3 plus 10 times, so 4.3 minus 4 is just 0.3, minus 6 times 0.3 to the second power. Oops. Second power, there we go. So I'm getting negative 0.54 for that. All right, now it says write the fourth order Taylor polynomial for g of x, which is the integral from 4 to x of f of t dt at x equals 4. This is just a fancy way to say, hey, you've got to integrate f of x. And remember the reason this is t and dt is it just has to be different than this. So g of x is approximately equal to, so go back to the original and just start integrating terms. So 7 becomes 7 times not just x, but x minus 4. So because we're centered at 4, right? So you're just adding 1 to your exponent and getting the linear term there. And then this will become minus 3 times x minus 4 to the second, and you divide it by its new exponent, which is 2. And then this will be plus 5 times x minus 4 to the third. And now that's over 3. We have to get up to fourth order, so fourth degree for this one. Minus 2 times x minus 4 to the fourth over 4. And it just says to write that fourth order factorial, fourth order Taylor polynomial, so I don't think I need anything extra. I'm looking at my answer key that I printed out, and I had like a little exclamation point there, but that's not right. It should just be over 4. All right, so that's it for part C. Part D, can the exact value of 3 be determined from the information given? So we can't say yes for sure. I can't say no for sure, but I can't say yes for sure because I don't know if 3 is in the interval of convergence. How far can we stray from the center of 4 before we get values that are not exactly equal to f of x? So can the exact value be determined? I'm going to say this is unknown, or you could say no, but this is unknown because there isn't an interval of convergence. They would need to give us that since we don't have a function to figure it out for ourselves. So the answer is no, we can't find f of 3. We're basically lacking information to find f of 3. If I found out that the interval of convergence, let's say it was anything between anything between 3 and 5, including 3, then yes, we'd be able to find it by just plugging 3 into f of x, and that would be the answer for the sum of the series. Okay, number 6, given a fifth degree, so n is 5, Maclaurin polynomial, c is 0. Here it is, the fifth degree Maclaurin polynomial, where the terms are alternating and going to 0. So, that's a nice piece of information. That means that if we're talking about error, it means that we can use the alternating series remainder instead of Lagrange. Use the third degree Maclaurin polynomial to estimate g of 1. Explain why this estimate differs from the actual value of g of 1 by less than 1 over 6 factorial. Okay, so first of all, what is P3? P3 of 1 is going to be our estimate for g of 1. All right, so that means instead of using P5, cut it off at P3. So that would be equal to 1 minus 1/2 plus 1 to the third over 3 times 4 factorial. So let's see what g of 1 is approximately equal to. So 1 minus 1/2 is 1/2 plus 1 over 3 times 4 factorial, which is 24. So I'm going to write all of that down, 0.5138 repeating. All right, and then explain why this estimate differs from the actual value. So they gave us this important information here. So we can use the alternating series remainder, which says, all right, we are trying to approximate g of 1. The difference between actual g of 1 and our P3 of 1 should be equal to the remainder of a third order polynomial evaluated at 1. And that should be less than or equal to the absolute value of the first neglected term. Now, it's not a 4 of 1 because, remember, the next term here would be a 5. So that's really a 5. Oops, an absolute value. And then we want to show that that's less than 1 over 6 factorial. Well, what is the first neglected term that we left off? We left off minus, but I'm just going to keep it plus, 1 to the 5th over 5 times 6 factorial, and that is definitely less than 1 over 6 factorial. All right, find the radius of convergence of this power series. So this is not quite our cosine power series because it's not alternating. So let's look at this radius of convergence. I need to do the ratio test. Limit as n approaches infinity of the absolute value of x to the 2n plus 2 over 2n plus 2 factorial times 2n factorial over x to the 2n. This is going to leave me with a 2n plus 2 times 2n plus 1, and the 2n factorial down here will cancel with the one on top, and we'll have an x squared. So this is something bottom heavy. X squared over a bottom heavy thing like infinity. X squared over infinity is 0. 0 is always less than 1. So find the radius of convergence. This series converges by the ratio test for all x that are elements of the real number system. You don't have to write that part. It asks for the ratio. So the ratio, or the radius of convergence. So the radius of convergence is infinity. All right, here's a little bit of 9.7 practice, just a little bit of review. So this says, determine the values of x for which the function can be replaced by the Taylor polynomial if the error cannot exceed 0.001. So this is showing me that it's not finding the values of n, it's the values of x. So this is showing me that, okay, we are using, to approximate cosine x, we are using a fourth order polynomial, right? So that tells me that I can use the error. I just saw a mistake on my original answer key. That means that I can use the remainder for a fourth order, right? So let's do this. So we're looking for the difference between cosine x and our fourth order Taylor polynomial at x. That should be equal to the remainder of the fourth order at x. That should be less than or equal to the fifth derivative. I realized I had a 4 there still at z. Times some x minus the center, which is 0, to the fifth power, over 5 factorial. And show that this error cannot exceed, we want to make sure it's less than 0.001. Now remember, this is a nice one because if f of x is cosine x, it means that f of n plus 1 will either be plus or minus sine or cosine. And so the max value for sine or cosine, no matter whether it's plus or minus or whatever, just is its amplitude. So the max is 1. So we can put a 1 in for the fifth derivative at z. And this would just be x to the fifth over 5 factorial, keeping that less than 0.001. Now, I'm solving for x here, so I'm going to multiply 5 factorial over to the other side. So x to the fifth is less than 0.001 times 5 factorial. I guess I could probably do this. I should be able to do this math, but whatever. We have that, so that's 0.12. I would need to fifth root both sides. Remember, fifth root is just like raise that to the 1/5 power. Or maybe I'll just leave it fifth root since it's going to be annoying to write out. So the fifth root would be anything, x can be anything between the negative version of 0.12 and the positive. Because this was an absolute value, I should keep this an absolute value. So when we fifth root both sides, we'll have anything between the negative fifth root of 0.12 and the positive fifth root of 0.12. All right. Determine the, oh wait, did I? Yeah, sorry. I did this with there is one other, I guess this didn't specify. I just did this with Lagrange error. What if we did this with, so this was Lagrange. I just kind of assumed. What if we did this with alternating series remainder instead? Because this is an alternating series, and the terms are decreasing in our interval of convergence. If x is some sort of decimal, these terms are decreasing towards 0. So let's just try this. If you did R4 of x, you could say, well, that just has to be less than or equal to the first neglected term. Now it's not going to be a 5 because the next term is going to be x to the 6th over 6 factorial. So it would be less than or equal to x to the 6th over 6 factorial. Keep that less than 0.001. And so that would be like saying x to the 6th is less than 6 factorial times 0.001, 0.72. And whether or not that's an absolute value, when you sixth root, even root something, you get your plus or minus. So yeah, anything between the negative sixth root of 0.72 and the positive sixth root of 0.72, that's what our alternating series remainder would give us. So on an AP test, they would specify whether you're using Lagrange, they'll say use Lagrange, or alternating series. And if they don't say use alternating series, they will lead you into it like they did here. The terms are alternating and going to 0, so then blah, blah, blah. All right, and I will be specific on a test as well. Determine the degree of the Maclaurin polynomial required for the error in the approximation of the function at the indicated value of x to be less than 0.0001. It says use n derivative to help, but no, don't do that because you're trying to find a pattern. If it's ln, we're trying to find a pattern for what these derivatives are. We don't have to plug n derivative on your calculator is only helpful when you're evaluating at the center. So, okay, let's take a look here. Where is this polynomial centered? It says Maclaurin. So C is 0. And we're trying to figure out the degree here. So we know that in general, we're trying to approximate f of 0.5. So that would be, we want the actual value of ln of 0.5 plus 1, or 1.5. We are going to approximate that with some sort of Taylor polynomial, evaluated at 0.5 as well. Not 1.5, because that's just plugging this in here. If that's confusing, just call this f of 0.5. Okay, and then that is equal to the remainder at some degree or order at 0.5. And let's use Lagrange because we don't know if this is alternating or not. I think it is, but let's just use Lagrange here. So that is less than or equal to the absolute value of some n plus 1 derivative at z. We'll have to figure out what that is, times the x value that I'm approximating minus the center to the n plus 1 over n plus 1 factorial. Trying to keep this less than 0.0001. So the big job is to figure out what is this n plus 1 derivative. Now, it's not a sine or a cosine. It's not just a nice e to the x. The derivatives will be different. So I need to start taking some derivatives and figuring out what the pattern is for the derivatives. So the derivative of ln of x plus 1 is 1 over x plus 1. The second derivative, and you don't have to evaluate at 0. You don't care about that. You're just trying to come up with a pattern for these expressions. So this would be negative 1 over x plus 1 squared. The third derivative would be 2 over x plus 1 to the third. And maybe we've done ln's a few times, so maybe you remember it's something about a factorial. So do as many as you need to see the pattern. I'm going to do one more. 24 over x plus 1 to the fifth. So always come up with the nth term derivative first. So how do these relate? It's over x plus 1 to the n. And then the top number is the factorial, the n minus 1 factorial. We don't care about plus or minus signs, so because all of this is an absolute value. What about the n plus 1 then? So just plug that in. Actually, I'm going to bring that up here. So what is this n plus 1 derivative of x? It's plug n plus 1 into that. It's just n factorial over x plus 1 to the n plus 1. And we're trying to figure out the max z. Now, z is some number sitting between the center and the approximation. And so you plug each of those extremes into this expression. So n factorial over 0 plus 1 to the n plus 1 versus n factorial over 0.5 plus 1, so 1.5 to the n plus 1. This is bigger because it's not getting divided by as large of a number. So we are just going to sub in n factorial in for this expression. And then this is 1/2 to the n plus 1, and this is n plus 1 factorial, keeping it less than 0.0001. Simplify a bit. So this is like 2 to the n plus 1 down here times just n plus 1, trying to keep it less than 0.0001. I'm going to use a calculator for this. You can also multiply things around. You could say, what is this? This is 1 over 10,000. So you could say 10,000 is less than 2 to the n plus 1. That's probably easier to see, like that. And then at this point, whether you're using the fraction version or this version, I'm going to use the non-fraction version, you would go to the table. I wouldn't just plug in a bunch of things. It's this times x plus 1. And I'm going to start my table at, it's already starting at 0. So when I go to second table, I'm looking for which value gets me higher than 10,000. It looks like it is 9. And yeah, and if I did this in the fraction version, I'd be over here making sure the decimal is less than 0.0001, but n equals 9. Now, when we are plugging, if we were to evaluate any of these derivatives, if you plug in 0, you're not getting 0 for any of these. So 9 will correspond with taking 9 derivatives will correspond with the degree 9 polynomial. All right. Last problem. Determine the degree of the Maclaurin polynomial required for the error in the approximation of the function to be less than 0.001. We're trying to approximate cosine of 0.01. So this is asking us, first of all, f of x is cosine x. So this is asking us to find the difference between cosine of 0.1 and some sort of Taylor polynomial that approximates 0.1. That's equal to the remainder at 0.1. I'm doing Lagrange again because this is an alternating series cosine, so I could use alternating series, but I just want to practice Lagrange because I think that's harder. So that's less than or equal to the max fn plus 1 at z times our x minus our center to the n plus 1 over n plus 1 factorial, and that's less than 0.001. Now, this one's kind of nice. When f of x is sine or cosine, we talked about this before, it means the max is just the amplitude, which is 1. So I'm just putting a 1 in for that. And then this is 1/10. So I'm going to move a 10 to the n plus 1 down here over n plus 1 factorial. Now, this should not take very much to get less than 0.001. You can also, this is 1 over 1,000, so you can also do 1,000 is less than 10 to the n plus 1 times n plus 1 factorial. This would be a fair one to make non-calculator because you would just be plugging in, like, it's only going to be 1 or 2 or something. So let's just see. So it's 10 to the x plus 1 times x plus 1 factorial. And if I go back to my window, I just need to exceed 1,000. So it only takes 2, n equals 2. Determine the degree. Now, think about this. Degree 2, will that, if n equals 2, does that correspond? Remember, your cosine x Maclaurin is 1 minus x squared over 2 factorial. So yeah, if we have to get out to 2 derivatives, that will correspond with a second degree. If the answer was n equals 3, it would be degree 2, because n equals 3 would be plus 0 x to the third over 3 factorial, so the degree would still be 2. All right, that finishes this assignment. Please come into office hours if you have questions about any of this or need clarification on anything.